Good day, this is Professor Will, CBMD PhD. Today's Monday, March 30th, 2020. It is 2:30 and 52 seconds a.m. Eastern Standard Time. And this is today's lecture on the relationships of alkalinity. So let's get started here. Alkalinity and pH relationships. Whether you are new to the water field or an old timer, alkalinity and pH relationships can still be confusing. Alkalinity is defined as the acid-absorbing property of water. The major acid-absorbing constituents that we typically deal with are hydroxide, OH, bicarbonate, HCO3, and carbonate, CO3 ions. Alkalinity testing. The P-M-OH-alkalinity tests are all related to these significant pHs. Acid is added until a pH endpoint is achieved, allowing the alkalinity components to be measured. M-alkalinity. The M-alkalinity is a measure of the amount of acid it takes to drop the pH to approximately 4.3. This would directly measure the amount of any bicarbonate, carbonate, and hydroxide alkalinity present, depending upon the starting pH. For example, if the starting pH is 9.0, the M-alkalinity test will measure the amount of bicarbonate and carbonate alkalinity, but will not measure hydroxide alkalinity because no measurable levels were present. P-alkalinity. The P-alkalinity is a measure of the amount of acid required to drop the pH to approximately 8.3. As can be seen, this would measure the amount of any carbonate or hydrocarbonate alkalinity present. Since the carbonate alkalinity is being converted to bicarbonate alkalinity, this test does not measure bicarbonate alkalinity. OH alkalinity. The OH alkalinity is a measure of the amount of acid required to drop the pH to approximately 8.3 after the carbonate has been precipitated out with barium and barium carbonate. You can also use an equation to calculate OH-alkalinity, depending upon the P- to M-alkalinity. The relationship that applies to most situations we see is OH equals 2P-M. This calculation should agree reasonably well with the OH-alkalinity test. If there is a difference, it may be due to interference from neutralizing amines, increasing the acid-absorbing ability of water. Conclusions. When thought of in terms of the presentation and the pH endpoints, hopefully you have a better understanding of alkalinity and pH relationships. On a second perspective, alkalinity is a chemical measurement of a water's ability to neutralize acid. Alkalinity is also a measure of water's buffering capacity, or its ability to resist changes in pH upon the addition of acids or bases. Alkalinity of natural waters is due primarily to the presence of weak acid salts, although strong bases may also contribute, i.e., OH in extreme environments. Biocarbonates represents the major form of alkalinity in natural waters, its sources being the partitioning of CO2 from the atmosphere and the weathering of carbonate minerals in rocks and soil. Other salts of weak acid, such as borate, silicates, ammonia, phosphates, and organic bases from natural organic matter, may be present in small amounts. Alkalinity by convention is reported as Mg/L, CaCO3, since most alkalinity is derived from the weathering of carbonate minerals. Neither alkalinity nor acidity have any known adverse health effects. Nonetheless, highly acidic and alkaline waters are considered unpalatable. Knowledge of these parameters may be important because 1. The alkalinity of a body of water provides information about how sensitive that water body will be to acid input such as acid rain. 2. Turbidity is frequently removed from drinking water by coagulation and flocculation. This process releases H+ into the water. Alkalinity must be present in excess of that destroyed by the H+ released for effective and complete coagulation to occur. 3. Hard waters are frequently softened by precipitation methods. The alkalinity of the water must be known in order to calculate the lime, CaOH2, and soda ash, Na2CO3, requirements for the precipitation. 4. Alkalinity is important to control corrosion in piping systems. 5. Bicarbonate HO3 and carbonate CO3 to the power of 2- may complex with other elements and compounds altering their toxicity transport and fate in the environment. To determine the alkalinity, a known volume of water sample is titrated with a standard solution of strong acid of pH value in the approximate range of 4 to 5. Titrations can distinguish between 3 types of alkalinity: carbonate, bicarbonate, and total alkalinity. Carbonate alkalinity is determined by titration of the water sample to the phenolphthalein indicator endpoint, or approximately a pH of 8.3. Total alkalinity is determined by titration of water sample to the endpoint of a methyl orange indicator, or approximate pH of 4.5. The difference between the two is the bicarbonate alkalinity. Note that only approximate pH endpoints can be given. This is because the exact endpoint is dependent on the total concentration of carbonate species in solution. The higher the total alkalinity, the lower the endpoint will be. Good day, this is Professor Will, CBMD PhD, on infectious disease and microbiology. Hope you enjoy listening and have a great day.